dear student, in the previous lecture I have discussed about the graphical solutions using a graphical calculator, and also I have discussed about how to use solver. In this lecture we can discuss sensitivity analysis. The agenda for this lecture is sensitivity analysis, in that if there is any change in the coefficient of the objective function, how that will affect our result. So, the another name for sensitivity analysis is post optimality analysis. So, sensitivity analysis is the study of how the changes in the coefficient of an optimization model affect the optimal solution. There are two ways it will affect. How will a change in a coefficient of objective function affect the optimal solution? Other one is how will a change in right hand side of a constraint affect the optimal solution. In this lecture we will discuss about the first case, that is if there is any change in the coefficient of objective function, how our solution, optimal solution get affected. This was the problem what we have used right from the beginning. Maximize 10s plus 9d, there are 4 constraints. So, this problem I will explain how to do sensitivity analysis. What is that sensitivity analysis we are talking about? If any changes in the coefficient of this objective function. For example, if the 10 may be changed, the 10 is the profit contribution, obviously the profit contribution will not be same. Sometime the profit contribution will be more, sometime the profit contribution will be less. But what will be effect of this profit contribution on our final solution? I have brought the same problem here. The optimal solution for the given problem, which is on the right hand side, S equal to 540 standard bags and D equal to, that is a deluxe bags, is equal to 252. So, based on the profit contribution figures of $10 per standard bag and $9 per deluxe bag. Suppose we later learn that a price reduction causes the profit contribution of the standard bag fall from $10 to say $8.5. So, sensitivity analysis can be used to determine whether the production schedule calling for 540 standard bags and 252 deluxe bags is still best. If there is a drop in price, our solution, that is S equal to 540 and D equal to 252 is the still best, or this drop in profit contribution will affect our final result or not. That is the purpose of sensitivity analysis. If it is solving a modified linear programming problem by changing the coefficient of objective function, as the new objective function will not be necessary. So, obviously you may ask this question, if the profit contribution is decreasing, we can simply change that coefficient value in the Excel, then we can get the final answer, but the redoing of the whole process is not required. So, the management would especially want to consider how the optimal production quantities should be revised if the profit contribution per deluxe bag were to drop. So, that is, if the price of the product is dropping, how that will affect our production quantities. There is another situation where the sensitivity analysis can be done. Suppose look at the right hand side of the constraint, 630 in the cutting and dyeing department, the total available hours is 630. That is what I have brought here. The another aspect of sensitivity analysis concern changes in the right hand side value of the constraint. In the problem, the optimal solution used all available time in the cutting and dyeing department and finishing department. You might have recollect from our previous lectures. So, this 630 hours, this constraint is our binding constraint. What is the meaning of binding constraint? We have utilized all 630 hours. This is happening to the finishing department also, that is how I brought in different colors. So, what would happen to the optimal solution and the total profit contribution if that company could obtain additional quantities of either of the resources. So, what is the meaning here? Suppose if the company is trying to bring some additional resources, they say +1 something. By bringing this additional resources, we need to check whether that will affect our final solution, or that will maximize, or that will affect our objective function, whether it is a maximization or minimization type. This is another way of doing sensitivity analysis. Just I am recollecting. There are two ways to do the sensitivity analysis. One is by changing the coefficient of the objective function. The second one is by changing the value on the right hand side of our constraints. So, sensitivity analysis can help determine how much each additional hour of production time is worth and how many hours can be added before diminishing returns set in. So, what is the meaning of this is, if I add one extra resources, whether the adding this extra resources is worth or not, how much it is worth. How much it is worth means how that will affect my objective function. And sometime what will happen when you keep on adding the resources, instead of it is positively affecting our objective function, sometime it will decrease. So, by adding more resources will not help for our objective function. So, that is the case of this diminishing returns. But in this class we discuss about the first case, that is if any changes in the coefficient of the objective function, how that will affect our final result. Let us consider how the changes in the objective function coefficient might affect the optimal solution. The current contribution to the profit is $10 per unit for the standard bag and $9 per unit for the deluxe bag. It seems obvious that an increase in the profit contribution for one of the bags might lead management to increase the production of that bag, and a decrease in the profit contribution for one of the bags might lead management to decrease the production of that bag. So, if the profit contribution is increases, obviously will company go for manufacturing more bags. If it is decreases, they will try to reduce the number of quantities manufactured. It is not as obvious, however, how much the profit contribution would have to change before the management would want to change the production quantities. So, what is the meaning of this? We know that already we got the result, that is S equal to 540 standard bags and deluxe bag is 252. If there is any small change in bag price, right, sometime the small change in bag price will not affect your production quantities. But if the bag price is significantly changing, so what it is required, sometime you have to change this production quantities also. So, what we are going to do in this one, how much allowable change is permitted, how much profit contribution, how much change in profit contribution is permitted, so that our solution remain changed. So, I am going to introduce the term called range of optimality. The current optimal solution to this problem call for producing 540 standard golf bags and 252 deluxe golf bags. The range of optimality for each objective function coefficient provides the range of values over which the current solution remain optimal. I think this picture will explain you clear idea. You see, this is our coefficient of our objective function. So, there is a lower limit for profit contribution, that is upper limit for profit contribution. So, this much change is permitted. So, this change will not affect your final solution, that is called range of optimality. Even though there is a variation in the coefficient of your objective function, that variation will not disturb your solutions. That allowable variation, the range of variation is nothing but your range of optimality. The managerial attention should be focused on those objective function coefficient that have narrow range of optimality, and the coefficient near the end point of the range. Obviously, when the range is very narrow, the management should provide more attention for that, because immediately your solution need to be changed, because if there is slight variation in the product price, that may affect your scheduling. So, with this coefficient, a small change can necessitate modifying the optimal solution. Now, I will explain this range of optimality graphically. We know that this region is our feasible region, which we have discussed in our previous lectures. This point is our where we got the optimal solution. So, now we will go back to the problem. The graphical solution of the problem with the slope of objective function line between slope of line A and B, the extreme point 3 is optimal. So, this point is optimal point for the given problem. See, there are, I am writing what is line A and line B. The cutting and dyeing department is called that line is, I am calling it line A. The finishing department corresponding constraint, I am calling it as line B. Okay. So, the range of optimality, so we have the objective function is this n, which is mentioned in the orange color, this is 10s plus 90. So, as long as the slope of the objective function is between the line A and B, right, as long as the slope of our objective function is between line and B, that will not affect our result. So, that will provide your range of optimality. As long as the slope of objective function line is between slope of line A, see that, which if it is slope of line A is this one, which coincides with the cutting and dyeing constraint line, and the slope of line B, which coincides with finishing constraint line, the extreme point 3 with S equal to 540, D equal to 252 will remain optimal. So, changing an objective function coefficient for S or D will cause the slope of objective function line to change. If there is any change in the coefficient of S and D, that will affect the slope of that objective function. In figure we see that such changes cause the objective function line to rotate around the extreme point 3. So, if any changes in the coefficient of objective function, that will cause rotating the objective function. However, as long as the objective function line stays within the shaded region, the extreme point 3 will remain optimal. What is the shaded region? This region. This region. Rotating the objective function counterclockwise. Suppose the objective function is in orange color. Suppose if you rotate this objective function counterclockwise, the slope to become less negative, okay, then the slope increases. Okay. So, when you rotate this way, when the objective function line rotates counterclockwise, because the slope is increased enough to coincide with the line A. So, suppose this line coincide with line A, we obtain alternative optimal solutions between extreme points 3 and 4. What will happen if this orange line is coinciding with this red line? So, what will happen in this region? Okay. See, all the points which are in this region will be our optimal solution. So, we will get alternate optimal solution. Any further counterclockwise rotation of the objective function line will cause extreme point 3 to be non-optimal. So, beyond this red line, if you rotate this orange line beyond that, so what will become? Then the solution point 3 will not be the optimal solution. Hence, the slope of line A, right, the slope of line A provides an upper limit for the slope of the objective function line. Now, we will see the other case, rotating the objective function line clockwise. Okay. Now, the objective function line is going to be rotated clockwise, causes the slope to become more negative and slope decreases. When the objective function line rotates clockwise, then slope will decrease enough to coincide with line B. What is line B? Which is in the red color. Line B, we obtain alternate optimal solution between 3 and 2. So, what will happen in this region, your objective function line will sit there. So, when it is coinciding, so all these points between 2 and 3 will become your optimal solution. You will get multiple optimal solution. Any further clockwise rotation of the objective function line will cause extreme point 3 to be non-optimal. So, if you rotate beyond this, so 3 will not be your optimal solution. Hence, the slope of line B provides a lower limit for the slope of the objective function line. So, now we got the upper limit and lower limit of your objective function line, so that the point 3 will remain optimal. So, the extreme point 3 will be optimal solution as long as slope of line B is less than or equal to slope of line objective function line is less than or equal to slope of line A. What it says that if the slope of your objective function line is between slope of line B and A, your optimal solution will remain same, that will not disturb your optimal solution. In given figure which is given on the right hand side, we see that the equation for line A is this one, line A, that is the cutting and dyeing constraint line, is like this. What is that line? Because it is equal to written 7 upon 10 s plus 1d equal to 630. So, I want to know the slope of this equation. So, I am going to rearrange, we know that very y equal to mx plus b, where m is the slope. Here y is nothing but your d, number of Dirac bags. So, I am going to write this equation to bring in this form, y equal to mx plus b, so that I can find out what is the slope. So, when you simplify d, okay, so you will get minus 7 upon 10 s plus 630. So, the minus 7 upon 10 says the slope of your line A. The 630 is the intercept of line A on d axis. Okay. Similarly, we will find the slope of line B. In figure we see that the equation for line B is this one, 1s plus 2 upon 3d equal to 708. So, 2 upon 3d, I am simplifying, when I brought on the right hand side minus s plus 708. So, when you simplify this, d equal to minus 3 by 2 s plus 1062. Now, this is your slope of your line B. Now, I am going to write our objective function in the generic form. So, P equal to CSS plus CDD. CS means coefficient of standard bag, CD means coefficient of Dirac bag. So, when I simplify, CD equal to minus CSS plus P whole divided by D. So, if I further simplify, I get D equal to minus CS by CDS plus P by CD. We hold the profit contribution for the Dirac bag fixed at initial value CD equal to 9. We know that it is 10s plus 9d. So, I am going to fix this value of CD equal to 9. We know that minus 3 by 2 less than or equal to minus CS by CD. So, instead of CD, I have substituted the value 9, less than or equal to minus 7 by 10. So, when I simplify, suppose I take only on the left hand side, when I simplify this, minus 3 by 2 less than or equal to minus Cs by 9. So, when minus get cancelled. So, the value of Cs what I am getting is 13.5. Similarly, if I take the right hand side inequality, minus Cs by 9 less than or equal to minus 7 upon 10. So, I am getting the Cs value 6.3. So, what we got? I have got the coefficient value for the standard bag between 6.3 to 13.5. So, what this number says that as long as the coefficient of standard bag is within this range, that will not disturb our final answer, that is a final solution. So, that will not affect our optimality. So, how we are interpreting? In the original problem, the standard bag had a profit contribution of $10. So, the resulting optimal solution was S equal to 540, D equal to 252. So, the range of optimality for CS tells for the given problem with other coefficients unchanged. What is other coefficient? The CD. CD is unchanged, that is what we have substituted CD equal to 9. The profit contribution for the standard bag can be anywhere between $6.3 and $13.5, and the production quantities of 540 standard bags and 252 deluxe bags will remain optimal. That is the interpretation of in the the slope which I have written in the previous slide. Even though the production quantities will not change, the total profit contribution, that is the value of objective function will change. The value of objective function will change due to change in profit contribution of standard bags. So, what is that our objective function? Z equal to 10S plus 9D. So, the value of this coefficient of standard bags, even though it is goes up to 13.5 and 6.3, our solution which we got it S equal to 540, D equal to 252 will remain same. That is the interpretation of this range of optimality. So, range of optimality for standard bags. Similarly, we can find the range of optimality for the deluxe bag also. That is what we have done it here. The same equations. So, here CS by CD, we know that CS by CD minus. So, the CS value I have substituted equal to 10 because our objective function is 10S plus 9D. So, I am going to find out what is the allowable range for the coefficient of the deluxe bags by assuming that the coefficient of standard bag is 10. So, the 10 I have substituted and then I have readjusted on the left hand side. So, I got 6.67 is lower limit and the upper limit is 14.29. So, what this number implies that as long as the coefficient of deluxe bags, this one goes up to 6.67 and 14.29, our solution, that is our S equal to 540, D equal to 252 remains same. Now, how to see this range of optimality in our solver output? So, I have brought the output of the solver. In the variable cell you see that the final value, that is our answer. This is objective function coefficient 10 and 9. So, here the allowable increase is 3.5, that is 13.5, allowed decrease 3.7. Similarly, for the deluxe bag, the currently it is 9, it can be increased 9 plus 5.2 and decreased by 9 minus 2.3. So, this is the place where you can get the range of optimality. So, the range of optimality is providing kind of a flexibility in the price changes. Even though the price changes, we need not bother about that, because that will not affect our optimal solution. Now, I will show this output in our Excel sheet. Now, this problem which we have solved in the previous class, we got the answer is 540 and 252. When I go to this answer report, you have to go to sensitivity report. Look at this location, that is final value is our answer. There is an objective function, there is an allowable increase and allowable decrease. So, this says the range of optimality. Now, we can see a special case in range of optimality. In cases where the rotation of the objective function line about an optimal extreme point causes the objective function line is become vertical. See, this green color says our given our objective function. Sometime if the objective function is vertical, there will be either no upper limit or no lower limit for the slope as it appears in the form of expression. So, we know that minus 3 by 2 less than or equal to minus Cs by Cd less than or equal to minus 7 by 10. To show this special situation can occur, suppose the objective function for the problem is 18 Cs plus 9d, say this is the new objective function. In this case the extreme point 2, so now this point 2 provides the optimal solution. So, rotating this objective function line counterclockwise this way, rotating in counterclockwise around the extreme point 2 provides an upper limit for the slope when the objective function line coincides with the line B. So, rotating the objective function line counterclockwise around extreme point 2 provides an upper limit for the slope when the objective function line coincides with the line B. Oh, this is our line B. We showed previously that slope of line B is minus 3 upon 2. So, the upper limit for the slope of the objective function line must be minus 3 by 2. There is upper limit, there is no problem. However, rotating the objective function in clockwise, suppose if you rotate this objective function clockwise result in the slope becoming more and more negative, approaching a value of minus infinity as the objective function line become vertical. In this case, the slope of the objective function has no lower limit. Using the upper limit of minus 3 upon 2, we can write minus Cs by Cd less than or equal to minus 3 by 2, that is the slope of our objective function. Following the previous procedure of holding Cd constant and the original value, that is Cd equal to 9. So, we have minus Cs by 9 less than or equal to minus 3 by 2. So, when you simplify this, we are getting Cs is 13.5. In reviewing this figure, we note that the extreme point 2 remains optimal for all values of Cs above 13.5. Thus, we obtain the following range of optimality for Cs at extreme point. So, the lower limit for this coefficient of standard bag is 13.5 and there is no upper limit. This is the special case of optimality when the objective function is vertical. Now, there may be another situation, simultaneous changes. What is the meaning of simultaneous changes? Coefficient of standard bags and coefficient of deluxe bags. So, simply compute the slope of the objective function minus Cs by Cd for the new coefficient values. If this ratio is greater than or equal to the lower limit on the slope of the objective function or less than or equal to the upper limit, then the changes made will not cause a change in optimal solution. If there is a simultaneous change, you have to find the ratio of minus Cs by Cd. If that ratio is within the limit, so our final result will not change. So, consider changes in both of the objective function coefficients for the problem which we are discussing. Suppose the profit contribution for the standard bag is increased to $13 and the profit contribution per deluxe bag is simultaneously reduced to 8. Now, both the things are happening together. Recall that changes for optimality for CS and CD both computed in one at a time manner. The way we have arrived CS, the range of optimality, because we have kept the coefficient of one, for example CS is kept constant, we found the answer for the D. Similarly, then D kept constant, so we got the answer for S. But now there is a simultaneous changes. So, CS is 6.3 to 13.5, now CD is 6.67 to 14.29. So, for these ranges of optimality, we can conclude that changing either CS to $13 or CD to 8, but not both, any one changes can take place, would not cause change in optimal solution S equal to 540, D equal to 252. Even though there are two changes are taking place, but we are considering only one change at a time. If there is any one change taking place at a time, both the changes are within the limit, that will not affect our optimal solution. But we cannot conclude from the ranges of optimality that changing both coefficients simultaneously would not result in change in the objective function. So, what will happen if there is simultaneous changes? So, that will affect our range of optimality simultaneous changes. We showed that the extreme point 3 remains optimal as long as minus 3 upon 2 less than or equal to minus CS by CD minus 7 by 7 upon 10. So, I brought in the number line 0 minus. So, as long as this ratio is within this limit, that will not disturb our optimal solution. If the CS is changed to 13 and simultaneously CD is changed to 8, the new objective function slope will be given by minus CS by CD. So, we will get minus 13 upon 8. So, minus 1.625. So, this minus 1.62 by minus 1.625 will go on this side. So, what will happen if both the things are changes are taking place simultaneously? So, you will not get the optimal solution. That means, you will get optimal solution, the solution which you are already having, that will be disturbed, because it is going beyond the ranges. Minus 1.625, because minus 1.625 is less than the lower limit of minus 3 by 2, the current solution S equal to 540 and D equal to 252 will no longer be optimal. So, in this case, by resolving the problem with the CS equal to 13 and CD equal to 8, we will find the extreme point 2 is the new optimal solution. Now, this is 2 is the new optimal solution. So, what we are learning from here, if there is a simultaneous changes, then we have to resolve the problem. So, sensitivity analysis, what we have discussed so far is any one value changes at a time, not both. If both the coefficients are changing at a time, we have to resolve the problem. Range of optimality, simultaneous changes. Looking at the ranges of optimality, we concluded that changing either CS to $13 or CD to $18, but not both, would not cause change in the optimal solution. But in a recomputing the slope of the objective function with simultaneous changes for both CS and CD, we saw that the optimal solution did change. So, what we are learning, if there is a simultaneous changes, our optimal solution will change. So, the result emphasize this fact that the range of optimality by itself can only be used to draw a conclusion about changes made to one objective function coefficient at a time. If both the coefficients are changing simultaneously, the range of optimality, the answer which we got, will not be valid. Now we will summarize what we have learnt in this class. We have learnt how will a change in the coefficient of objective function affect the optimal solution. Then we have learnt a new term called range of optimality. Then we have seen if there is a simultaneous changes of coefficient of objective function, how that will affect our optimal solution. Okay student, the next class we will learn how a change in right side value of constraint affect the optimal solution. So far we have seen if any changes in the coefficient of objective function, how that will affect our optimal solution. But in the next lecture, if the right hand side of our constraint is changing, how that will affect our optimal solution. Thank you.